Okay, are you guys ready? Hello?
The screen
Yes.
will be shared in just a minute.
Yeah, the recording has started. It's streaming live on YouTube. So, whenever you guys are ready, please start.
Vishesh?
Yes, Tarun, you ready?
Yeah, I'm ready.
Thank you. A human mind is unbounded. Seemingly impossible number of thoughts and ideas take birth as we move through time. There is only one other thing that can match its magnificence: the universe. A happy evening to everyone present here. Long time ago, when the universe was just born, the predominant conditions were hostile to the clumping of baryonic matter. There was something that provided the baryonic matter a refuge where it could accumulate and build all the humongous structures that we see today, as well as what we are made of. If humanity's understanding of the early universe is right, what is that exquisite stuff that nested baryonic matter? That is dark matter. Do we have dark matter all around us? Beside you, beside me? If not, where else is it? So, most of these seemingly endless questions or the pieces of puzzles that we have, the unanswered, mystified. Up ahead, we have Rama, who is going to brief you all about the history and the evidences that support dark matter claim.
Good evening, everyone. Let me start by saying dark matter has a very rich history. It goes way back to 1880s. Lord Kelvin, in his talk, estimated that the mass of the galaxy, which he determined is different from the mass of visible stars. He concluded that many of our stars, perhaps a great majority of them, may be dark bodies. The first to suggest the existence of dark matter using stellar velocity was Dutch astronomer Jacobus Kaplan in 1922. Jan Ott hypothesized the same in 1932. Now we know that the history of dark matter mainly consists of the mass of galaxies and velocity of stellar objects. Now we will see about the Virial theorem. Virial theorem is used to have to estimate the mass luminosity relation of galaxy. In the 1930s, Fritz Zwicky, who was a famous Swiss astronomer, he was measuring the motions of galaxies within the Coma cluster, which contains more than 1,000 galaxies. He noticed something interesting. The galaxies were whizzing around the cluster really fast, and it didn't make sense to him. Since these galaxies are gravitationally bound, he calculated the mass of Coma cluster using the speed of galaxies. The total value of mass luminosity of Coma cluster was 100 times than they expected. Thereby, he postulated the existence of something holding the galaxies together, a dark, invisible mass, dark matter. Now, I will talk about the rotation curve of galaxies. In the 1970s, Vera Rubin, another famous American astronomer, studied the rotation curve of galaxies in her thesis. That is, do objects within the galaxies actually rotate? Objects here refers to stars and gases. At the same time, Ken Ford had built a spectrograph which is used to measure the speed of stars inside the galaxy from the center to the visible edge. She, ob- she observed the rotation curve of Andromeda galaxy. There's a simple mathematical equation equating centripetal force and gravitational force. We get an equation which now let's see what the final equation is. So the final equation you can see in the top left corner and the graph below it. This shows that V is inversely proportional to root r and proves that when an object has more mass, the more gravitational pull it should have, and the curve represents the further the object is from the center, the slower it should travel in orbit. For example, the planets in our solar system. The planet is from the further the planet is from the sun, the slower it should travel. But that makes sense, right? But that's not the case with galaxies and clusters. The velocities of objects orbiting the center of galaxy, rather than decreasing as a function of distance from the galactic center as had been expected, it remained constant to a very large extent. Now I will show you about the rotation curve of ATC 319. Like the graph which you saw before, the curve was decreasing, but after collecting all the data of Andromeda galaxy and plotting it in a graph, the line did not go down. It kept on going and kept on increasing as a flat curve. Why? She concluded that they had to be more mass, otherwise the galaxy would have fallen apart. So where have been assumed that there is a halo of invisible matter surrounding the galaxy, and this mass provides the force to speed up the orbits. In the left side, the graph is the rotation curve of ATC 3198. You can see the decreasing curve, that is the disk that is expected result, but it turned out to be a flat curve which is on top, and the curve between the flat and the disk is the rotation curve of halo present in the outer region of galaxy. Similar observations were found for many galaxies, including our own Milky Way, and the results turned out to be a flat curve. Now, let me show you me. Now, Vishal is going to talk about CMB and the hot gases in cluster.
Hi, I'm going to talk about cosmic microwave background. So, after the Big Bang explosion, the temperature of the after the Big Bang kind of started decreasing, right? So after that, the atoms, the subatomic particles, started to get together and form atoms. So during this process of fusion, electromagnetic wave was released. So as the time passed over the over billions of years, due to the red shift effect, the wavelength increased, and that corresponded with the microwave spectrum. So now whatever you see in the left image is oldest radiation from the early stage of Big Bang. So you see the fluctuation in the graph. Those fluctuation is a small tiny changes in the temperature. So what does this mean? This means that the dark matter is actually contributing to the cosmic microwave background, to have this huge fluctuation. My dark matter contributes to this denser region. So as the dark matter is much denser, the temperature also increases. And another thing is that oscillation between the matter, gravitational force of matter, and pressure of photons, it would be much irregular if there is a large amount of dark matter, because dark matter interacts with the gravitational force. And yeah, there's recently it's been observed that this fluctuations, it's been recently found that there has been a fluctuations in the universe, and that's the observable universe. Now I would like to talk about hot gas and clusters. So researchers have found that there is a existence of hot gas in the clusters. So the question remained, why and how does this hot gas hold together, as the hot gas particle move very faster, and their temperature is very high. So since their temperature and the speed of the particles are very high, they emit X-ray radiation. Because of that radiation, with the Rostag took this image on the right hand side. And the question, as okay, sorry, I was muted. Okay, so the question remained, how does the hot gas remained intact inside the clusters? So the mass of the stars in the clusters were not enough to support, to hold this hot gas in the clusters. So the dark matter was one of the answers that could be answered by such way. Also, recently, where the Chandra X-ray Observatory calculated there was how much distributions were there in Abell 2029 galaxy clusters. So it's a galaxy cluster name, and they found out that it matched with the data which we see today. That is 25% of dark matter, 70% of dark energy, and 5% of matter, that is luminous matter. Oh yeah. And now I would like to talk about nucleosynthesis. So nucleosynthesis is nothing but a it's a process of a making of a new atomic nuclei using neutrinos. Neutrinos are nothing but protons and neutrons. When protons and neutrons come together, they form deuterium. Deuterium is a second isotope, it's a second isotope of hydrogen. So this process happened just couple of 100 seconds after the Big Bang, and after deuterium becomes stable, they get together. Lithium and helium starts to form. Now it takes a really long time for carbon, oxygen, and nitrogen to form, as helium should be in a high pressure to form carbon, oxygen, and nitrogen cycle to happen. So that happens only when the helium is in the star. So what does it say about dark matter evidence? Well, when you take the prediction from when you take the data from the elements that elements of the percentage of the elements from this early stage of Big Bang, and compare with the existing data, taking 5% of the current universe matter, you see that it matches. So it gives a bigger clue that nucleosynthesis is also supports the dark matter existence. So now I would like Tarun to take over this and talk more about evidences. Thank you.
Hi everyone. I think Rama and Disha did an amazing job explaining about the previous evidences before me about the Virial theorem or the CMB. But for all those skeptics out there who need a little bit more evidence to believe in dark matter, I'm here just for that. So gravitational lensing. Another strong piece of evidence is gravitational lensing. So what I'm going to talk about right now is about what is gravitational lensing, how is it related to dark matter. I'm going to give an example about how about the galaxy cluster Abell 2218 and the Einstein rings present in it. So, what exactly is gravitational lensing? So, any day, a typical Wikipedia definition would give you this. A gravitational lens is a distribution of matter between a distant light source and an observer that is capable of bending the light from the source as the light travels towards the observer. This effect is known as gravitational lensing. Well, let me break it down for you. Well, we all know how intelligent Einstein was, and gravitational lens has a lot to do with Einstein's general theory of the all famous Einstein general theory of relativity. Um, Einstein managed to figure out how mass and spacetime affect each other in four-dimensional space. So mass tells spacetime how to curve, and spacetime curve tells mass how to move. So in this picture out here, you can see a four-dimensional space which is displayed in three dimension. This is the space-time fabric, and what the idea over here is this mass You could consider this as a huge mass, be it a star or whatever. And this mass is able to bend the space-time over here. And it's just to give you an idea that mass affects space-time and space-time affects mass or matter. So imagine you are in Earth right here, chilling, and you are observing a star. And the light from the star travels straight until it reaches this point where it gets curved to reach you over here. But for you over here, you will not see this curve, and you will observe that the star is over here. And this is called gravitational lensing, which occurs due to mass. So in case this mass was not in this particular place, the light from the star would directly travel in a straight line to you to reach in this place. But when it's over here, it takes a bend over here to come reach you. And this is basically gravitational lensing broken down. So how is it related to dark matter, you might ask? Let me just tell you, we just really scientists are really lucky that we know that in some parts of the universe, the gravitational lensing effect is produced even when there is no presence of normal matter. That is, we don't actually need a visible mass to do gravitational lensing, and even invisible mass can do gravitational lensing. And that we thought are the presence of dark matter in that region. So this is a beautiful image of the Abel supercluster. So what you see over here are different galaxies, here. All these are different galaxies. And I would like you to pay attention to these ring-like structures that you see over here. From here, all these smears that you see around the galaxy cluster. So these rings that you see over here is actually termed as Einstein rings. So what you see over here is because of gravitational lensing. So this, because of the mass of the supercluster Abell 2218, the light from the galaxies behind the supercluster is bent or distorted, just as how you would see through a lens that you might have experienced in your lab in your younger ages in school or college. So that is how these galaxies, the light from these galaxies are bent and sometimes even repeated in places. So how does this help us? One, Einstein rings. Like as to gave you a picture of it in the previous cluster. These rings that you see over here can actually be used to calculate the mass of that particular supercluster. So Einstein managed to devise a mathematical equation where the radius of the particular Einstein ring is directly proportional to the square root of 4 times the gravitational constant, the mass, divided by the square of light, speed of light. And so here you can actually see that this mass over here is that the square root of mass over here directly proportional uh, to the radius of the ring. And this actually helps us calculate the mass which is there in the particular galaxy cluster. And when we did that, we found a very interesting idea. What was expected, that is, the estimated mass by calculating the mass of the stars and gases, was actually lower than the actual mass that was calculated from gravitational lensing. And this is very interesting, as well, it gives us an idea that there is more matter than there is visible stuff that you can see in that cluster. And that mass that we see over there is called dark matter. So I have a simulation of gravitational lensing over here with me. What you see over here is, in this area is a group of galaxies in a cluster, and the light emanating from these galaxies are bent by this concentration of dark matter in this region, and it is bent to reach you who is beyond this particular plane. So this is a similar thing which you can see in the Abel cluster in real time, and these rings that you see are called Einstein rings. I hope this gives you a really good understanding of what gravitational lensing is and how it is used to detect dark matter. Okay, moving on. The bullet cluster. The Bull cluster is that one evidence which is adored by all particle dark matter theorists. So it is just that, when the Mon theorists were parting after the discovery of their discovery, the Bull cluster landed on their roof like a meteor, destroying their dreams. Okay, so Bull cluster is basically a colliding colliding galaxies. I'll show you a picture of the Bull cluster. So what you see over here is the picture of a bullet cluster. It's a superimposed picture of the bullet cluster. All these galaxies that you see, all these lights that you see over here is an optical image which is taken by the Hubble telescope. And this particular image that you see, the pink image and the blue image, was an image taken by the Chandra X-ray telescope, which was superimposed on this image to create the final image. So I'd like you to pay attention to this part. So you might be wondering what this pink color might represent. This pink color, all of you might know that in a galaxy cluster, what mostly makes it up is obviously galaxies, but the major part of the galaxy cluster is made up of hot gases. That almost makes up almost two-thirds of it. So when the two galaxy clusters collide, from one, say, moving from this direction and another moving from, say, this direction, the whole all the material in it, including the gas clusters, including the hot gases, also collide. And because this gives a similar reaction when you pour water against each other, there's a friction which is created, due to which there's a drag which is created amongst the hot gases. And the gases from both the clusters are lagging behind compared to the galaxies in the cluster. And also, you might be wondering what this blue part over here might symbolize. So this blue part is actually representing what where the most of the mass of the galaxy cluster is located. This was obtained by weak gravitational lensing, and which it proved that these blue areas are the regions where most of the mass is located. But you might wonder what's wrong with that. Since I told you that hot gases make up most of the galaxy clusters, more the matter, more the mass, and hence more gravity. But in this scenario, the most gravity was not in this place, but instead in this place. So this gave us to a really strong evidence that there was dark matter in this place, which in the galaxy cluster, which actually moved past each other in the other cluster without interacting with them or the normal matter. Let me show you a simulation. So what you see here is again the same image of the bullet cluster, the superimposed image. Let me speed this up. And now this is the normal picture that was taken by the Hubble telescope. And when you superimpose the X-ray image of the hot gases, this is what you get. So this is the contour diagram which was drawn to show where the most of the mass is located. And clearly we can see most of the mass is located in these blue regions where we predict there is dark matter. So this is a simulation of how the collision occurred. This is the dark matter region, and this is the hot gas. So as you can see, the dark matter moved without interacting, without changing, completely freely to each other. But when you notice, the hot gas is being dragged behind due to friction. This about concludes gives us the strongest evidence that dark matter exists in this universe in the larger scale. Uh, next we have Kritika talking about properties of dark matter.
Yeah, that was an interesting stuff from Tarun. Now I'll be telling about the properties of dark matter. Dark matter cannot be detected by observing electromagnetic radiation, and gamma rays are produced when dark matter particles decay or when they collide with or annihilate with each other. Dark matter cannot be consisted of baryons, and some theories also suggest that dark matter cannot consist of light particles. This is because light particles were relativistic at early time and thus they fly out of small scale density perturbations. Mass limitations of dark matter particles is such that it should range from 10 power minus 31 GeV per c square to 10 power 50 GeV per c square. And the calculation of collision between clusters which cause bullet formations showed that the interaction between dark matter particles should be less than 35 kiloparsec per hour for a typical scattering cross section of 1.75 into 10 power minus 25 centimeter. And now Atulya will be continuing.
Okay, coming to the classification of dark matter, these are the dark matter candidates which classified with respect to the thermal velocity. They are cold dark matter, hot dark matter, and warm dark matter, short as CDM, HDM, and WDM. So far, the theories range from saying that dark matter is called hot or warm, with the most widely accepted theory being the lambda CDM theory. Currently, the simplest cosmological model that fits the experimental observation is the CDM model, lambda CDM model. Okay, now we can look briefly about the types of dark matter, the cold dark matter. So, there are the cold dark matter is the particle that are created with very low and zero velocity. To be more precise, velocities are much slower than the speed of light. We have mentioned dark matter before the reference to the CMB. CMB means cosmic microwave background, and it was the longest matter component of the opaque universe. And it is the dark matter density that produce filament structures that we see in the universe today. But this is only work if the dark matter doesn't fly off at the near to the speed of the light, as neutrinos do. In this respect, they are said to be cold, that is, cold dark matter. As the cold refers to the particles moves very slow, and the dark indicates it interact weakly with ordinary matter and the electromagnetic radiation. So, if the dark matter is pure cold dark matter, then the structures form a bottom type way. That is, first stars form, then the galaxies, then the cluster group, and the clusters, and finally the superclusters. This is what we see now, right? So, we can literally tell that dark matter is believed to all the cold dark matter. So, there is bunch of dark matter candidates such as WIMPs, supersymmetric particles, superstrings, Kaluza-Klein particles. So, telling about the Kaluza-Klein particles, it's the form of Kaluza theory. A scientist, Theodore Kaluza, he set forth the idea of unifying graviton and electromagnetism within five-dimensional spacetime in a paper from the beginning of 1990. So, this theory explains when we are explaining in a simple manner to imagine, think about a telephone wire, and to see, to us, we can see it as a wire, which is in one dimensional. But to an ant, it can walk one dimensional, cross or around the spiral patterns within the telephone wire. So, the ant at its smaller level precedes an extra dimension, which we cannot see. This is Kalusa's idea. So, Saga will explain more about this. And these candidates are only hypothetical, and none of these are actually yet known to the exist of nature, but they are possibly predicted by some unverified attractive theories, and these are the attractive theories in the particle physics. So, we are moving to the dark matter. When coming to the hot dark matter, it moves at very high speed and can be theorized only by the relativistic equations. The hot dark matter can travel faster than the cold dark matter because the HDM particles are theorized to be the lower mass. So HDM contributes very less percentage to the dark matter, and its proposed candidates were neutrinos. So in terms of their application, the distribution of HDM also helped to explain how clusters and superclusters of galaxies formed after Big Bang. So there are two theories that exist. that those are the congregate around the individual members of the cluster of visible galaxies, and the other one is that encompass the clusters as a wall, because that CDM possesses a lower free velocity, that it could be the source of smaller galaxy size lumps. So, however, the data from the cosmic microwave background radiation as measured by COB satellite is highly uniform, and also the HDM being the salt substance in explaining the cosmic galaxy formation no longer viable. It places a larger umbrella of mixed dark matter theory. So the candidate of the hot dark matter particle is the neutrino, and they have small masses. They are theoretically interact by weak interaction and the gravity, but due to the feeble strength of the forces, they are difficult to detect. So, okay, then moving to the warm dark matter. The warm dark matter is intermediate to the hot dark matter and cold dark matter. And to be considered the word warm, they would have primordial velocities comparable to the size of dwarf galaxy. So the mass of the particle lies in between that of HDM and CDM. So the most common WDM candidates are sterile neutrinos and gravitons. The winds, when produced non-thermally, could be candidate of warm dark matter, but in general, however, the thermally produced winds are called dark matter candidates. So over the last decade, the warm dark matter has repeatedly proposed as an alternative scenario to the standard cold dark matter, and the warm dark matter to maintain as a significantly different alternative to the CDM, that is called dark matter, more evolved protection mechanism leading to the multiple dark matter components or a gradually decreasing small scale power spectrum has to be considered. So these terms, that is CDM, HDM, and WDM, do it refers to the temperature of the particles, but the speed of that which the dark matter particles were moving when the galaxies began to form billions of years ago. So the scientists study dark matter by looking at the effects that it has on visible objects. So the next topic, Kritika will explain about the supersymmetry. Thank you.
Now we will go deep into the theoretical models of dark matter. Dark matter is explained in many models like lambda CDM, MOND, Kaluza-Klein, tensor vector scale gravity, etc. But now it will be one of the most interesting, mind-boggling yet so controversial theoretical model of dark matter. That is the supersymmetric string theory of dark matter. So in this, you'll learn about string theory and principle of supersymmetry. And we'll find answers for why dark matter doesn't interact with normal matter and electromagnetic waves, and why it affects us only through gravity. Could dark matter be made of exotic supersymmetric particles, etc.? Now, Sagar will be explaining in detail.
The dark matter candidates that you observed was more of a teaser to what will be explained ahead. So keep your thinking caps on. Until then, Saga will bring us with the theories which actually explain why and what dark matter could be. And that is a could because we are still clueless. Saga, go ahead.
So now, supersymmetric string theory of dark matter is really a very big theory. So we'll first learn about some basic ideas. So the standard model. The standard model comprises all the fundamental particles which we have detected till now. Fundamental means which can't be divided further. So the standard model has two parts. That is, you can see here all the left ones, first three rows have spin of 1/2. They're called as fermions. And the right part, they are integer spins. So they are called bosons. So in these fermions, there are two types. They are quarks and leptons. So this is the idea of standard model, which comprises all the detected and proved fundamental particles till now. So going to next, the four forces. So we know the four forces of nature. They are gravity, weak force, electromagnetic force, and strong force. Here's an image of these forces. So it's saying that in big after Big Bang till 10 power minus 43 seconds, all these forces were merged to one super force. Can you imagine how strong that would be? However, as temperature of this universe began to decrease, the fundamental forces started to being separated. So the first force that is separated was gravity, which determines the motion of all the cosmological objects in our space, and then strong force, which holds the quarks together and forms protons and neutrons, and it also helps in binding the nucleus of atom. And next it was weak force, which helps in radioactive decay, and then electromagnetic force, which determines the motion of charged particles in electric and magnetic field. So it also the the standard model also assigns some of the force carriers for these forces. They are gluons for strong force and W and Z bosons for weak force, photons for electromagnetic force. But for gravity, there is no force carrier assigned still. So sad. But my idea of supersymmetry, that is theorized by Michio Kaku, will give the answer. So now we know that 20th century was witnessed to give the rise of the greatest theories in physics. One was general relativity and other was quantum physics. So these theories explain the motion of uh, the particles in their own realms. General relativity explained the motion of particles in cosmological scale, and quantum physics explained the particles in the quantum realm. But shouldn't there be one idea, one master equation that should control the whole universe? So that will be given by string theory. So string theory is also called as theory of everything. It says that all the fundamental particles are made of one-dimensional strings. So all the fundamental particles are made of one-dimensional strings. Then how will they differ? And moreover, the length of these strings are 10 power minus 35 meters. They're very minute in the order of Planck's length, and the tension force is 10 power 44 newtons in the order of Planck's force. So there are also two types of strings. One is open strings and closed strings. So these forces differ in two ways. That is, four ways. That is open or closeness, fundamental. So in this manner, elementary particles will be differed. So here's a picture of a proton that shows two up quark and one down quark. So we can see that up quarks has similar type of strings, but down quark has different type of open string. So this is how the string differs in different particles. So our universe is made of tiny vibrating strings. So now if universe is made of tiny vibrating strings, how can we see matter? So we know that matter is made of fundamental units called atoms. They have nucleus surrounded by electron surrounding them. Then nucleons have protons and neutrons made of quarks. So these quarks, as suggested by string theory, says that they're tiny vibrating strings. So this is how matter is according to string theory. So, but this theory is also really controversial. So why? Because the math of this theory doesn't work in 4 dimensions, as we all know, but it requires 7 additional dimensions of space to exist in our universe. So that means then our universe is 11 dimensional, 10 for space and one for time. So this is really controversial because many people don't believe this. But here's one small video clip which shows how we can perceive this 11-dimensional universe. So in this video, the grid represents our world, our 4D world. But from this circle, small circle is to fourth dimension. And if we see there are some additional curled up dimensions coming out. So this is a 7-dimensional space which you're seeing. This is called as Calabi U space. So our universe is 4-dimensional, and additional to that, there are 7 extra dimensions. So this is how we can perceive our 11-dimensional world. So this image is actually uh, so this image, what you saw, is actually showing our universe in the Planck's order. That is 10 power minus 35 meters. When we zoom that, our universe will be like this only. So where we can see 11-dimensional universe. So this is how the string theory tells about our universe. So actually, many scientist community doesn't agree, but we say that they are not able to be detected, but because only minute particles like strings can overlap in those 11 dimensions, not us. So the weakest force is not really weak actually. How means we know that gravity is a weakest force, but string theory gives an answer for that. Gravity has force carrier called gravitons. The even gravitons will be made up of strings, right? So those strings have zero amplitude. So since they have zero amplitude, it makes the gravitons to move across dimensions. So gravitons are the only particles that can move across these 11 dimensions. So that's why gravitational force will be diffused to 11 dimensions. That is why we see it as a very weak force. So here's a small video clip which shows how gravity escapes to other dimensions. So we see that when two gravitons interact, some gravitons will escape. So now supersymmetry. Supersymmetry is one of the principle of dark matter superstring theory. So it says that since all the fundamental particles, even force particles and matter particles are made of strings, they have to be related, right? So it treats force and matter identically in the equations of standard model. So equations of force and matter are identical. It also argues perfect symmetry between these particles. So particles of force have integer spin. Particles of matter have half integer spin. So it says that there is one symmetry, supersymmetry between them. So it also says that each particle in a standard model has a super partner associated with it. So how we can perceive this is, so above the plane, all are standard model particles which we have detected, but each particle has some cousin particle associated with it. So we can see that they have different sizes. So super partners have same charge, different mass, where heavier one is unstable. That is, it decays very early, and their spin differs by 1 by 2. As here, it argues perfect symmetry between half integer and integer spin. So their spin also differs by 1 by 2. So this is the image of minimal supersymmetric standard model. This standard model incorporates all the supersymmetric particles and standard model particles. So here we see that in standard model particles, they are quarks, leptons, bosons. But in supersymmetric partners, they are named in different manner. Quarks have quarks as superpartners. Bosons have bosinos. Leptons have sleptons. So all these fermions have an S starting in the superpartner name. So these bosons have INO as ending name. So these are the partners will be named. And moreover, you should know that these quarks which have integer spin are force carriers in supersymmetric particle in model. But these gluino, photino, xeno, vino, vixino, All these are matter particles because they have half integer spins. So dark matter particles could be supersymmetric particles. We'll find out how. So now we know the basics of this superstring theory. Now we'll come to the actual part. So in our early universe, it says that there were equal number of all particles, it seems. So Susi postulates that in early stage of universe, there were equal number of all types of particles, which were super partners of each other. One super partner will be heavy and other one is light, as I said. So the heavier one will be unstable, but the lightest of those, called as lightest supersymmetric particle, that is LSPs, will be left behind. That could make up DM. So that's why DM doesn't decay now. We'll see how. So uh, in early universe, dark matter particles interacted to give standard model particles. So in early universe, we know that the space was very compact. In the beginning of Big Bang, the space was very compact. In that space, dark matter particles were interacting to give standard model particles, and standard model particles were interacting to give dark matter particles. So there was equilibrium in this reaction. But as the space expanded exponentially, the rate of dark matter to standard model particles decreased. That's because as the volume expanded, the particles being very small, they couldn't interact with each other because they're very far away. So that's why they couldn't interact. So that time, what those dark matter was left, that is that is the one which we are seeing now. So then the abundance of this dark matter should become a constant. So we'll also find out what is the abundancy of this dark matter. So there is this relation. Now we know that dark matter abundance is inversely proportional to rate of its annihilation. So when calculations were done, we get the abundance of dark matter to be this value. So there is rigorous calculations done to get this value. So when this value was got, the same calculation was done on supersymmetric particles. So supersymmetric particle abundance will be inversely proportional to the annihilation of supersymmetric particles. So when the same calculation was done, the result was striking. That is, the abundance of supersymmetric particles was similar to that of dark matter particles. So this should suggest that dark matter is made up of supersymmetric particles. So what we'll understand from these slides is that dark matter is made of LSPs, as I said. They are not baryonic and they're made of LSPs, like neutralino and gravitino. These are some of the examples of LSPs, and during the candidates time, we'll learn about some other candidates. So now we know that electromagnetic wave doesn't interact with dark matter. Why? Because electromagnetic wave, as explained by Kaluza and Klein, requires a total of 5 dimensions. What Kaluza told was, now we know that gravity is caused due to curvature in 4th dimension. So similarly, he said that in 5th dimension, if there is some curvature caused, that will interact with electromagnetic waves. So that will gives rise to the motion of electromagnetic waves. So he brought the idea of 5th dimension. So then electromagnetic waves can interact with particles less than 5th dimension. But we know that dark matter particles are higher dimensional. So that is why electromagnetic waves can't interact with DM, because DM is a 11 dimensional particle, whereas electromagnetic waves, they are related due to 5th dimension curvature. So these are the images from Kaluza's paper, which shows that the 5th dimension curvature, which results in movement of electromagnetic waves. So then we also know that the dark matter affects normal matter only through gravity. Here is a visual representation which shows that. So we see that dark matter lies in some higher dimensions, but it is affecting our normal universe, which we perceive as 4 dimensions. So Strings of normal matter mainly occupy 4 dimensions. As we know, even we all occupy 4 dimensions, 3 of space and 1 of time. But these strings of dark matter mainly occupy higher dimensions. So that is why matter cannot interact with dark matter. We, as in bullet cluster, you saw that when two galaxies collided, only the hot gas part has friction and they reduced in velocity. But dark matter doesn't interact at all. So they just slipped through each other. So that is why we see that dark matter doesn't interact with normal matter at all. And dark matter is higher dimensional particle, as I said, which can interact with normal matter only through gravity, which is capable of traveling across dimensions. So as I said, dark matter has will affect only through gravity, and moreover these gravitons, as said by string theory, only that particle can travel across dimensions. So that is why it interacts with normal matter only through gravity. So I end my presentation on this with this quote by Michio Kaku, which says that the best theory comes from string theory, and matter is nothing but a vibration of string in higher level. So this is the quote by Michio Kaku. Thank you. And now we'll see Raksha presenting more about candidates.
Thank you, Sagar. So far, my teammates have spoken about the different evidences of dark matter, and they've done a great job at it. So now we know that dark matter actually does exist. But the next question is what this dark matter is actually made of. Obviously, no one knows it yet, but there are a number of theories that is like a few particles are very simple, but few are very exotic, and I'm gonna just walk you guys through few of the more prominent ones. In the next slide, there is this table. Sagar, next slide. Yeah, so there's a table of classifications of different dark matter hypotheses. So it is mainly divided into three groups: baryonic, non-baryonic, and modified gravity. So baryonic dark matter is dark matter that is said to be made of baryons, as in quarks. Under that, we have machos, sims, and primordial black holes. Next up, we've got non-baryonic dark matter, which says that dark matter is actually made up of something that is not a part of our standard model, as in something exotic. Under this, we have WIMPs, superWIMPs, axions, dark photons, and sterile neutrinos. Finally, we have modified gravity, which states that our understanding of gravity itself is flawed, as we need in the stellar level to understand these different effects. So out of all these theories, I'll be talking about 7 of these. I'll just briefly walk you guys through everything. First off, we have machos or massive compact halo objects, which was the first theory to be theorized. Machos are basically objects that emit like little to no radiation, and they're non-luminous. And then these just drift around, and they're not a part of any planetary system. They have a huge range of mass from 10 power minus 18 to 100 solar masses. These machos basically consist of black holes, brown dwarfs, neutron stars, and unassociated planets. We can detect these machos through gravitational microlensing, which is basically a phenomenon where if a non-luminous object comes into within our line of sight, in front of a luminous object, we see a flare of light, and through this we can detect these objects. But then, after studying CBM and using baryonic acoustic oscillators, we realized that there isn't enough baryons in the universe to actually make up dark matter. So considering that matches actually exist, they still can't completely explain the effects of dark matter. Next up, we have axions. So these axions were, yeah. So these axions were basically theorized to explain the strong CP problem by Helen Quinn and Roberto Pecchiai in 1977. What is the strong CP problem? So the problem is that neutrons don't follow CP symmetry. CP symmetry is something that states that an event or an object, when you change the charge or the parity, the results should be the same. the same. Now in the equation, in the second part of the equation, we have a theta next to g square, right? So for CP symmetry to actually be followed, theta should be a constant. But to explain the neutrons properties, what we do is we consider theta to be a dynamic field. So when theta is a dynamic field, the particle of this dynamic field is said to be an axion. These axions move slow, and they barely interact with each other, and so they are components of cold dark matter. Their mass ranges from 10 power minus 5 to 10 power minus 3 ev by c squared. Now axions have this property where if axions are passed through like here high magnetic field, a strong magnetic field, they convert into photons and vice versa. So what we're trying to do is we're either trying to create axions by passing light through a strong magnetic field, or we're trying to collect the axion from the universe, because dark matter is all around us, right? So we're trying to collect that, and we're trying to pass that through a strong magnetic field, hoping to detect light. ADXM, PVLAS, and IAXO are few of the experiments and observatories that are doing the same. Moving on, we have WIMPs, or weakly interacting massive particles, which are the most researched upon particles for all out of all the different theories. So these were hypothesized in the 1970s to interact with weak nuclear force, as the name suggests, and they are constituents of cold dark matter. So they interact only through gravity and not through electromagnetic like they don't interact with electromagnetic waves. Their mass is about 100 GeV. So two theories that support the existence of WIMPs is supersymmetry and WIMP miracle, both of which Sagar already spoke about. So by supersymmetry, we think that WIMPs are actually the supersymmetric partner of Z boson and Higgs boson. Now, to detect WIMPs directly, we use LHC and CDMS, but we haven't been able to find anything yet. And the indirect detection of WIMPs is detect the gamma rays emitted by WIMPs when they interact with each other. Arshi will be explaining more about these detection techniques. Moving on, we have SIMS, which are basically the opposite of WIMPs. They are strongly interacting massive particles. So these particles, as the name suggests, interact strongly, and they are components of hot dark matter. And then they were actually originally hypothesized as a solution for ultra high energy cosmic ray problem and absence of cooling flows in galactic clusters. These actually later scientists realized that there are better ways of explaining these two problems. So SIMS were kind of but they're still in the running for hot dark matter. Yeah, hot dark matter. And then they are made up of standard down antiquark with strong nuclear force, as in gluon, binding them together. Next, we have sterile neutrinos, which are basically they have a right chirality. So the neutrinos that are in our standard model are basically neutrinos with left chirality. So these are possible constituents of warm dark matter. They are neutral, massive, and they don't interact with electron waves. They are unstable, but their half-life is longer than the age of the universe. And because they have zero charge and zero hypercharge, they don't react with weak nuclear force, strong nuclear force, or through electromagnetic force. Hence they like only interact through gravity, and their mass is unknown because we haven't been able to detect much in this field. Moving on, we have dark photons. Dark photons should basically be constituents of dark energy, but what they do is they interact with Higgs boson and they gain mass through that. And the production of dark photon in the universe is a non-thermal process. So there's a lot of research, and there are a lot of papers that suggest that LIGO might be sensitive enough to actually detect these dark photons, and their mass is hypothesized to be between 10 power minus 13 to 10 power minus 11 eV. Finally, the last candidate I'm going to talk about is primordial black holes. So these black holes are said to be formed in the first nth century. These were formed mostly due to inconsistencies in the density of the universe. So whenever there's an inconsistency in the density, it collapses upon itself and a black hole is formed, and it is said that hot plasma at this time of the universe actually helped the formation. So to actually stay stable, they are usually in a system of system of binaries, and they collide very slowly. So these were seven of the more you know more research upon candidates for dark matter, but none of them are exactly concrete, and we don't know yet. But a lot of detection is trying, people are trying to detect this, and Arshi will be explaining about the different techniques they're trying to you know they're using. So yeah, thank you.
Thank you, Raksha. So far we have seen about what is dark matter, what are the types of dark matter, what are the evidences of dark matter. So now we will be looking into the detection of dark matter particles. So there are various methods in which scientists are trying to detect dark matter. The experiment can be mainly divided into direct detection and indirect detection. And the third one is the collider search, which I will be talking about it later part. So first come the direct detection method. So let's say if dark matter is made up of subatomic particles, then billions of these particles should pass through per square centimeter of Earth every second. So direct detection aims for this kind of hypothesis. Now the question arises that how scientists are actually trying to find it. So direct detection is mostly can be divided into cryogenic detection technique or the noble liquid technique. So one thing I would like to clear is here is that all those experiments that I will be talking about is basically meant for the detection of specific type of dark matter candidate, that is WIMP, weakly interactive massive particle. Okay, so moving on to the cryogenic detection technology, the experiments such as CDMS, CREST, etc., are doing this kind of using this kind of techniques. On the other hand, noble liquid detection uses Zeppelin, Xenon, DEEP, etc. So cryogenic detectors operates at temperature less than 100 millikelvin, trying to detect the heat generated when particle collide with another atom. Whereas in noble liquid detector, it detects the light produced by the particle collision in liquid xenon or argon. So if I want to convey in one sentence what the direct detection technique is about, so it's about how to detect the recoil, how scientists try to detect the recoil of nuclei due to collision of dark matter particles. So in the next slide, I will be explaining about the setup for the Xenon 1T experiment. That is the noble liquid detection technique, one of the noble liquid detection technique. So here basically you can see there is a tank which is filled with pure liquid xenon, 3.2 metric ton liquid xenon, and the experiment is conducted in negative of 96 degrees Celsius of temperature. So what we generally expect here is that the WIMP particles to collide with the xenon atoms and thus produce a faint UV light signal. So these signals should be captured by the highly sensitive photosensors which are embedded at the top and bottom of the tank. So yeah, so far we have not get we have scientists had not get any fruitful result, but it doesn't mean that the experiment was completely failure. In fact, I want to share a fact that it has detected something that has never been seen before. So xenon has total 9 isotopes, and one of them is xenon 124. So scientists expect that the half-life of xenon 124 is some trillion years. That it takes trillion years to decay into the next particle, that is tellurium 124. But from this experiment, from xenon 1T experiment, scientists found out that the half-life of xenon 124 is 18 sextillion years. That is 18 into 10 to the power 21 years, which is trillion times more than the age of the universe itself. So you can see the experiment can any experiment can never be a complete failure. It's like you are searching for something else and you are getting something. And I must also include that it is the the you can say the longest half life of any element discovered so far in direct detection. So yeah, now here also a main problem in this kind of detection is the cosmic rays. That is, the cosmic ray can create distortion in the data. That's why these kind of detection or experiments are generally underground. So next come the indirect detection part. While direct detection is mostly ground-based experiment, indirect way is just the opposite to that. In this process, scientists look for the byproducts of DM annihilation in space, that is, the gamma ray and the high energy neutrinos. So talking about the gamma rays, from the standard model, we know that particle and antiparticle annihilate each other and gives off gamma ray. So for this reason, scientists focuses on region that has high chances of high density DM particles. Like example is the center of any galaxy. So this kind of detection will strongly suggest the existence of WIMP particle. So gamma ray detection, the telescopes that are working on it are Fermi-LABs, HESS, etc. So yeah. On the other hand, if there is also a chance that dark matter particle may accumulate inside the Earth and while passing through it. So this could produce a distinct kind of signal. We can capture these signal on the Earth itself in the form of high energy neutrinos. So high energy neutrino telescopes such as Amanda, IceCube, etc. are working for these kind of signals. So in the next slide, I will be explaining about the process going on in the ice cube. Yeah. Okay, so in the right side, you can see the image taken by Fermi-LAB, that is the gamma ray telescope, and it shows the emission of gamma rays at our Milky Way galaxy. So the center, it predicts that the center of the Milky Way galaxy should be the main source for these kind of detection, since most of the complex activities goes at the center of the galaxy itself. Yeah. So talking about the ice cube experiment, so ice cube is basically an laboratory which is at the South Pole, that is at the Antarctica, and what scientists here try to detect is the neutrinos. So neutrinos are as I mentioned earlier, the byproducts are said to be the byproducts of the WIMP particle annihilation. So they are also known as ghost particle because they can travel anywhere in the universe. Even now, if now neutrinos, millions of neutrinos can be passing through your body each second, and you do not know about it. So they are also quite rare and hard to detect. But here, what scientists try is that if they want to detect neutrinos, so they what simply they do is they try to place a thin transparent film at the part of neutrinos, so that there might be chances that out of millions of neutrinos passing, at least one neutrino may collide with the nucleus of that thin film and thus creates a distinct signal. So this principle works here. So the ice cube is consists of many detectors which are placed at the underground of ice layers, and these detectors search for the neutrinos as they passes. And if suppose one of the million neutrinos collide with the detectors, thus it creates a kind of mini nuclear explosion. So these nuclear explosion give rise to charged particle, and these charged particle emits specific blue lights. So the detector at underground the ice layer detect these blue light, and thus the scientists analyze these blue lights, like what is the pattern of the blue light, and from these data the scientists study that what is the path traveled by the neutrino, and what is the energy carried by the neutrino, and even from where the neutrino has arises. So these kind of questions can be answered in these experiments. So here also there is a problem that in these indirect detection method, many astrophysical sources can mimic the signals too. like millisecond pulsars or any big events in the interstellar cloud can mimic these kind of signal. So scientists are still working upon finding for specific signal for these detections, and let's hope for the best. So yeah, next is the collider search. So I am not going to explain deeply into what is going on in the collider, in any collider. I'm just going to make a comment on that uh, apart from these two types, that are normal detection and indirect detection, there is also a third type, that is the particle accelerator, which is also trying to detect the dark matter. So with the proton beam which is produced because uh, in the collider, so because dark matter interact less with ordinary matter, so it may be found indirectly as a missing energy and momentum that escapes the detector. So for the main point here is that I want to convey is that for any discovery from the collider itself, it should match with the theoretical value too. Then only we can say that the detection is confirmed. So yeah, at the conclusion of the detection part, I just want to say that till now the scientists are not yet get any proof for any kind of detection of dark matter particle. But if it is to be found, then it will be a groundbreaking discovery. Okay, so yeah, that's it. Now, just to give you a glimpse for the alternative theory for dark matter, I would like Vivek to take over the slides.
Oh, it was so much of information only about dark matter. So let's have a quiet change of topic. It's a last topic, but not the least. Yeah, this story started due to the problem of rotational speeds in galaxies, right? So let's go back to the early studies. There comes a Mond. Mond theory is nothing but it is a modified Newtonian dynamics theory, which was introduced in 1983 by Mordai Milgrom. Yeah, the Mond theory came up to solve the mass discrepancy in galaxies and to avoid the concept of non-baryonic matter. There was a ongoing questions that why the rotation speeds of stars are constant in the arms of the galaxies. So dark matter theory you have seen already that what it explains. So uh, but there was other theory which is more it comes up with the idea without dark matter, and it tries to modify the Newtonian dynamics and tries to explain the problem. So at larger radii, the dependency on gravity was modified to 1 by r, which was originally dependency on 1 by r square. And the acceleration due to gravity on the objects of the outer edges of galaxies is altered. Next, here, here we can see the equation which is modified. Here an equals a mu of a by a naught. An is nothing but the acceleration in Newtonian dynamics, like normal acceleration we have. And it was slightly changed, and there was a thing added, that is mu of x. Mu of x is a function, and it is a function which is yet to be defined, and mu of x is the extra function which was given to the modified Newtonian dynamics. So here a naught is the constant, it's a fundamental constant, which is 1.2 into 10 to the power minus 10 meter per second square. Yeah, we can see here force equation which was given by Newton's law, that was F equals m, net force was equals ma, but here it is slightly changed, where acceleration is added with a mu of x function, where x stands for a by a naught. For non-relativistic conditions, mu of x goes to equals 1. In non-relativistic conditions means the conditions where speed speed of object is not nearly equal to the speed of light, lesser than that. Yeah, but for acceleration slower than the value of a naught, the value of mu of x changes accordingly, as we can see in the equation above. Here, uh, actually, the Mond came up to explain the function, the main important graph, which we can see here. That was a graph for radius and velocity curve. The red curve we can see was for the Newtonian dynamics, and the blue curve was for a Mond. Here we can see change in the curves. Actually, the observed curve was the Mond curve. We can see here that it slightly increases and remains constant. But according to Newtonian dynamics, it has to reduce. But it's not the case. So, Mond cannot be the genius theory. Why? Vishesh is gonna explain that.
Thank you, Vivek, for introducing Mond to us. But this is the time for anti-Mond people to rejoice, as we will be discrediting the whole Mond theory itself. So the very first evidence, and which is like the evidence which cemented the presence of dark matter, was the bullet cluster observations. And the one very main reason that Mond fails is it does not add on the concept of extra mass that was required, whereas the bullet cluster observation required some quantity to produce a gravitational effect as to hold on the galaxies. So here Mond failed and dark matter explained. Okay, over to the next one. The second one is gravitational lensing. When the huge galactic clusters come in our way, we actually observe the bending of light. But the amount of bending or the magnitude of bending does not coincide with the amount of bending that we expect while. Okay, sorry for the delay. There's some like network issue here. So the galactic clusters actually must hold some more mass that was actually required to produce the amount of lengths that we observe. But Mond again does not add mass, so cannot explain the magnitude or the extra magnitude of lensing that we observe. And dark matter, with its addition of mass, does just that. So to the Mond theorists, sorry. Okay, so the next evidence that we have is the filament-like structures that were observed at the very huge levels at the cosmos. The filament-like structures is actually produced due to the presence of dark matter, or that's what the dark matter theory suggests at least, that the gravitational force of dark matter was able to hold on to the galactic clusters or the galaxies within it and form dense regions like pockets, you may call, where there's actually more concentration of baryonic matter, and other regions where there is less amount of baryonic matter, causing voids that we observe. So if that is told, these observations just solidify our claim on dark matter's existence that was predicted by the lambda cold dark matter theory. And as Carl Sagan once said, somewhere something incredible is waiting to be known. This very okay, thank you everyone for going with listening to us whatever we said, and the very quote by Carl Sagan is the reason why I actually that motivates me to learn more and like more delve into dark matter. And as we got into the note of thank you, well, I would like to thank the admins at Equinox for providing us this opportunity. And also, here are the names of people who were the spokes in our wheels that actually helped us roll smoothly throughout the Equinox program. Thank you, each one of you, for being a part of T1A Dark Matter. was a great time with you all, and kudos to all of you. T1A Dark Matter signing off. Thank you.
Amazing job, guys. That was wonderful. I mean, that was a lot of information that you guys have put together in a very compact, very wonderful way. And you covered more, width than I thought you would. You covered like a lot of topics. So, very, very well organized. Thank you so much. And yeah, great, great consistency throughout the Equinox program. You guys were always enthusiastic, always, working on it. So good teamwork. Yeah, kudos to Vishesh.
Yeah, same. Pass on the kudos to all of our team members. We'll share it. Thank you, Sitara.
Amazing job, Vishesh. And T1A, very good job. Totally impressed by the entire presentation.